So let's start the class officially now. So in this chapter 1, we will learn basic results. So these are the basic results we will learn in the chapter 1. Excuse me. So we will learn random experiment, sample space first, and then event, probability of an event. Sorry, an event and axioms of the probability, and then we will learn probability. So we will learn. Okay, we will learn conditional probability independent of events, random variable, probability mass function, geometric distribution, expectation and variance in this class. Okay, so these are the topics we will cover in this chapter 1. Okay, so I'm not going to cover all the subsections in chapter 1 to 6, but I will cover most of the required concepts in chapter 1 to 6. Okay, so in this today's discussion, in this first class, we will discuss what is the probability mean and what is the random experiment mean, how we can define it. So first we will get the idea of what is random experiment mean, and then we will define it mathematically. And finally, we will learn sample space, how to write a sample space for random experiment. So we will discuss these 3 concepts today. So that means basically we are covering this one. Okay. So in class 1, we will cover first bullet point. Okay, so let's see what is the probability means. Okay, so there are some situations we don't have exact confidence to say it's something going to happen or not. Okay, so for example, so this is the most basic example I can give in this class, and we will use this one time by time. Suppose you are toss a coin. Okay, so suppose you are toss a coin once. Okay, so suppose you are toss a coin once, so you will get either head or tail. Okay, so these are the output you can get from this experiment. But until you get the output, you don't know you are going to get a head or tail. Okay, so we can give another real world example. Okay, so this is example 1, and we can think another example of a real world example. Okay, I will stick with the color. Raining tomorrow. Okay, so this is a real world example. We don't know until tomorrow is coming up. We don't know it's going to rain or not. Okay, so those are some situations we cannot exactly say what is the outcome is. Okay, but we know what's going on. Okay, so for example, when we are tossing a coin, we know it's going to be head or tail. If it is raining tomorrow, we know it is going to be not rain or rain. But until the situation is occurred, we don't know. Until tomorrow is coming, we don't know it's going to rain or not. Okay, so in this kind of situation, we say it's a random phenomena. Okay, so this is a random phenomena. Okay, so we don't know outcome of the situation, the phenomena. So probability used to study this kind of random phenomena. Okay, so we don't know the output, so we can use probability to get some idea or to quantify the random phenomena. Okay, so more specifically in this course, we will study probabilistic models. So you are going to learn probabilistic model. So those are mathematical models for random phenomena. So you are going to model the random phenomena. Such models we can use to quantify. You can find the probabilities, or you can predict the situation. We can predict the random phenomena, or get some explain for some extension on the random phenomena. So those are the goal of learning this, taking this class. Okay, so you will learn probability to explain a random phenomenon. Okay, so I think the idea is clear now. So now we can we have to define a concept called random experiment. So the random experiment is the call in this class we call a random phenomena. So the random phenomena is called a random experiment in this class. So let's define the random experiment in mathematical way. Okay, so the random experiment is a process that results is exactly one of the collection of possible outcomes. Okay, so the random experiment is a we should know all the collection of outcomes, and results is going to be one of those collection. And we don't know the actual outcome until it's going to be happen. Okay, the actual outcome cannot be known with certainty in advance. Okay, we don't know the outcome until the experiment is performed. So those are two characteristic of a random experiment. It should the result should be one of the collection of all possible known outcomes. So the outcomes are known, but we don't know the results until it's happened. Okay, let's go to the next slide. Okay, so first I will give an example here. Our popular example is tossing a coin. So example is the example is tossing a coin. This is the technical example. So in this class, I will provide technical standard example and real example as well, and training. Okay, so these are the examples for random experiment because we know the outcome. So we know the outcome for this one. It is going to be head. So now on I will use head, H for head, and tail, T for tail. And when it's raining tomorrow, it's going to be rain or not rain. Okay, so there are only two outcomes in here. Okay, so the another technical example is tossing tossing two coins. Okay, so these are some technical examples, tossing two coins. Okay, and one more real world example, random experiment. Okay, so here we have three examples. So we can say okay, okay, let's say football team A wins tomorrow. Okay, so winning or losing a game also a random phenomenon. So these are some experiment for some example for random experiment. Now let's see what is the sample space concept mean. Okay, so the sample space means we are going to list all possible outcomes in a random experiment. So this is I think it should be explained in here. Okay. So the sample space is the all possible outcomes in a random experiment. Okay. So when we are listing sample space, we will use omega to denote the sample space. So this omega is the notation. So this can be omega. So that's how you can read it or pronounce it for the letter. This is a Greek letter omega. So we will use the Greek letter omega to denote the sample space. And within the two curly brackets, we will list all the possible outcomes. So here, list of all possible outcomes in a random experiment. Okay, so if you take our popular example, which is tossing a coin. So your sample space will be head and tail. And if I take the real world example, which is raining tomorrow. So in this experiment, omega will be rain or not rain. Okay. So now let's talk about more examples. Okay. So before going to the examples, I have one question for you. Okay. So before going to more examples of writing sample space, I have one question. Okay. Okay, so first question. So you can provide the answer for this one in discussion form. So the question is, okay, so this is the question. Sun is rising. Okay, so this is the experiment. My question is this experiment okay, is this a random experiment? Okay, so please answer this question. So I will provide this answer through the pool or pool everywhere or in the discussion form or maybe both. So please provide your answer for this question. Sun is rising tomorrow. I want to know, is this a random experiment or not? Okay, so we said random experiment has two outcomes. Two rules. First rule is result should be exactly one of the collection of possible outcomes, and output cannot be say until it's happened. Okay. So this experiment is sun is rise tomorrow. My question is this random experiment or not? Okay, so please provide the answer for this one, and I will explain more examples to write down the sample space and check whether those are random experiment or not. Okay, so let's consider the first example. First one is tossing a coin 3 times. Okay, so you have, you can think this one, you have 3 coins in your hand. You are tossing this one 3 times. So the first question is this a random experiment or not? Okay. So this is, what do you think? Is a random experiment or not? Yes, this is a random experiment. Okay, so that's why it's mean here. This is a random experiment. Why? Why? Because we can say because first rule, the outcome is one of the collection of known outcomes. Okay, so I will list all the outcomes later. Okay, so the second one, we cannot let's say predict. Okay, so that's a good word, predict. We can exactly say we cannot predict the exact outcome until the experiment performed, until we toss 3 coins. Okay, okay, so now let's list the sample space for this random experiment. So if it is a random experiment, we should be able to list all the possible outcomes. Okay. Okay, so let's list these outcomes in this sample space. So when you're tossing 3 coins, you can get head, head, head in all 3 coins. Okay. So this means H in first coin. I will use different color here. Okay, so this first H means head in first coin. Second head means head in second coin. And this H means head in third coin. Okay, now similarly, I think you should be able to write down all the outcomes. So in this case, you should have 8 outcomes because you have head and tail in one coin. So 2 to the power 3, you will get 8 outcomes. Okay, so you will learn how to get the sample space without writing it later. Okay, so but for now, you can list all the outcomes and count the number of outcomes in the sample space. So here head, head, head. So now I can get head, head, tail, head, tail, head, tail, head, head. So I move 1 tail for each position and then now bring 2 tails and move it to each position. And finally, I have 3 tails. Okay. So these are the all possible outcomes you can get if you toss 3 coins at once. Okay. So in here we can see 8 outcomes are there, and your output will be, your outcome will be any of these 8. Okay, we don't know until we toss these 3 coins once. We don't know which outcome we will see. Okay. So if you have any question on these examples, please meet me during my office hours, so then you can understand deeply and more well in this examples. Okay, because it is very important to know how to figure it out, experiment is random or not, and then how to find the sample space for the random experiment as well. Okay, so let's consider the second example. Consider tossing a coin until a head appears and recording all the result in order. Okay, so now we are going to toss the coin until head appears. Okay, we don't going to stop until we see the head. Okay, so this is a random experiment. Okay, because okay, so this because first one, the outcome will be a the outcome from known set of outcomes. Because you know you are tossing a coin, coin has head and tails, so you know which outcome is going to be show you. So you will see head in the first toss, or you will see tail and head in the second toss, so and so on. So you know what outcome you will see, but until you are doing the experiment, you don't know which outcome you will get. But the outcome cannot predict Okay, so you cannot say you are going to get head in first toss, or you cannot say you are going to get tail in first toss and then you will get head in the second toss. No, you cannot say something like that because this is a random experiment. Okay, so the now let's list the sample space. Okay, so when you are writing omega, you don't want to say it's sample space because that's the notation we are going to denote the sample space. So if you use omega, I know it is you are meaning the sample space. So it's omega equal. Now think about the situation. Okay, so you are tossing a coin until head appear. So if you toss once, and if you want to stop by once, so you should get head at first trial. So okay, if you are doing twice, means you get tail in first trial and head in the second trial. Then you are stop. Or you are going to get head tail in the first trial, tail in the second trial, and head in the third trial. You stop. Or you can get tail, 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 and head. So 2 tails, 3 tails, and head. That's when you are going to get the head in fourth trial. And you can repeat this one until you get head. So this is going to infinity. Okay. So you cannot list all the outcomes here, but we know it is infinity. Okay, so now let's compare the previous sample space and the sample space. And here we see so we toss 2 outcomes with 3 times, we will get 8 outcomes. And this is a, okay, so here this is a finite sample space. So we know how many outcomes in the sample space. So in that case, we can say it is finite. Okay, so now let's check whether the second example. So we don't know how many outcomes in this sample space. So this is infinite sample space. However, you can count this one, 1, 2, 3 likewise. So you can say this is countably infinite sample space. Okay. So this is countable infinite, and the previous example finite. Okay. And this is, you can count this one, 1, 2, 3 likewise up to 8. So this is a discrete sample space as well, because you can count it. Okay. And this is countable infinite, but it is still countable, so that means this is discrete. If something you can count, mean it is discrete, and if you can count it down to the infinity, so that means it's countable infinite. Okay, so that's how you can figure it out. It is infinite or finite sample space. Okay, so this is my third example. So if you have any question, please let me know. Okay, I'm assuming you have a better knowledge now how to write down the sample space for a given question. Okay, so the next example, in a long stretch of an oil pipeline, the number of leaks in a given year seriously enough to require a special repair crew is considered a random experiment. Okay, so in this one also a random experiment, because we don't know how many leaks we will show in a given year, and the number of leaks will be not going to be unknown value. Okay, so we know it's a countable value. Okay, so let's write down the sample space directly for this one. Okay, so the sample space omega will be, we can see 0 number of leaks, it's possible, 1 number of leaks, 2 number of leaks, 3 number of leaks, and so on. So we don't know how many leaks you can see in the pipeline, but we know it is a countable infinite set. Okay, so this is something similar to, sorry, the previous one. This is countably infinite sample space. Okay, omega, and this is a discrete one as well. Okay, so this omega is discrete and countably infinite. Hopefully that makes sense as well. Okay, the last example, something different than what we discussed so far. Last example is lifetime of a bulb. Okay, so measuring the lifetime of a bulb is considered a random experiment. Okay, so because until we measure the lifetime of a bulb, we don't know what is the lifetime of that bulb, and we know it's not going to we know the outcome. Okay, so we know the lifetime of the bulb should be somewhere between some number of values. Okay, so let's write down the omega for this question as well, but in this case you are measuring a lifetime of a bulb. Okay, so the lifetime of a bulb, you will get a time. It can be a second, but most of the cases is going to be hours. Okay, so this is most of the time hours. It's very hard you will get the other unit. So here you are measuring the lifetime of a bulbs in terms of hours, second, or days. Okay, so in this case, your sample space is going to be a continuous one. Okay, see this? Okay, so oops. Okay, so suppose this is a timeline. Oops, I want to draw a line. Okay, so suppose this is a timeline. So definitely your bulb should cannot have a minus lifetime. So it should at least start here, 0 time. It can be hours, second, or day, and it can go over to the infinity. It can go up to the infinity. So that's mean your omega is not going to be, cannot be list, but we can show in a interval notation. Okay, so it is going to be 0 to infinity. In the timeline, your omega, your sample space can be anything between 0 to infinity. Or if you want to use a curly bracket here, you can use this notation. T should be greater than or equal 0, and T is in real number. Okay. So this is the mathematical way you can write this one. So this notation means T in real number line. Okay, so this R means the real number line. So that's not just R, it is crypted R. So something like this. So this is the notation for real numbers. Okay. And in this case, we can see omega is not going to be the discrete because we cannot count. We cannot count the values in here. Okay. So we cannot count the values in omega. So this is, in this situation, it is called continuous omega. Okay. So continuous sample space. Okay. So we did 4 examples. So one example is three examples related with discrete sample space, and one example is related with continuous omega. Okay. So in next class, we will discuss events and probability of an event and axioms of probabilities. So, and for I think that's the good place to stop the class today. Okay. So if you have any questions, please contact me through my email address, or I will provide this, I will post this question. Okay, so this question in discussion form and pool everywhere. So you can provide your answers to this question and go through this video. And if you have any questions, please visit me and let me know if ask questions. Okay. So thanks for your time and attention. I'm look forward to meet you in my next video 2. Okay, thank you.